So your pages from your packet for today say this is a big thing. This is the biggest thing in the packet, and it's typed in red in all capital letters. This is the stuff. Just like I told you that using experiments to calculate rate constants was the thing in chapter 14, calculating equilibrium constants, equilibrium values, given initial information is the big thing for 15. So we're going to do a problem together today, and we're actually going to do another one from the problem set because this is the thing. That you use charts called ice charts, which are going to come back with your acid and base calculations next packet also. So we're introducing these ice charts today, figuring out why they're ice charts and how to use them. Basically, we're doing a problem and doing a problem. A mixture containing this stuff is where we start. Consisting initially of 3 moles NH3, 2 moles N2, and 5 moles H2. In a 5-liter container, we're going to heat it to 900 Kelvin, and it's reaching equilibrium. I give you one concentration at equilibrium, and I want you to find the others. So we're going to find the reaction. A lot of times you're going to be given the reaction or easily be able to tell which direction it's going. Because remember, with equilibrium, it could be moving either direction. We're going to set up the ice chart and put in our knowns. That's your initial, the I in ice. We're going to use the known values we have to solve for an unknown. And that'll be our change. And then E in ice is equilibrium. Initial, change, equilibrium. We're going to use the stoichiometry of the reaction to move forward from there. And we can, if we need to, calculate Kc or Kp given these values. So let's try this one. First and foremost, I have moles, I have liters, and it isn't 1 liter. So we're going to need to calculate our molarities, our concentrations, as moles per liter. 3 divided by 5, and 2 divided by 5, and 5 divided by 5 will give me my concentrations. So my concentration here is 0.60. Concentration here, 0.40. And concentration here, 1.0 moles. That's just because them is moles and we divide to get to molarity. So there we go. It says to write the reaction. I need to know whether I'm making NH3 or breaking down NH3. So I look at these, and there's a little more information in the problem that's going to set it up. It says that my equilibrium concentration of hydrogen is 0.352 molar. It's way higher than that here. So I must be using hydrogen. And that's where I get the reaction N2 plus 3H2. I wrote it as a one-directional reaction because that's the one I'm looking at. I'm looking at that direction of the equilibrium. It doesn't matter if you put in the equilibrium arrow or that. I'm just saying because I start out with 1.0 molar hydrogen and I end up with 0.352, I know it's being consumed as a reactant, not made as a product. So my ice chart from this reaction, I wrote ICE down the side. I could write initial change in equilibrium. I think in the pages I'm going to show you for your packet, we've got those. But for this, it just says ice, which is nice. And above it, I'm going to put the participants in the reaction with their coefficients. That's a thing, with coefficients, and this is in your packet. I've got N2, and I've got 3H2. And I like to do this. I like to put a mark on my chart that divides reactants from products. A lot of people don't do that. I do. And it's just me. It's just the way I like to see it because then I know I'm subtracting on one side and adding on the other of that break line. And I fill in my info from above. I actually could do, I could actually do that. For my H2 and my NH3. What you'll notice is I didn't do anything with the coefficients with my initial values. I wrote them here, but I didn't include anything with the 1 and the 3 and the 2 when I wrote down my initial concentrations. I literally copied them from the problem. I have one more piece of information I can include. That. So this is what I know. This is where I'm starting. And now I'm going to start thinking about what happens. Use known values to solve for one unknown change. I know how my concentrations had to change to get here. I know that my reactants had to decrease, and my product in this case, or products in other cases, had to increase. That's definitions of reactants and products. So let's say that this reactant decreased by a value we'll call X. And if you scroll down, or if I scroll down, there we go, I've got them filled in for you. And the using X chart, since my coefficient is 3, I have lost 3X there. I'm losing from the reactants, and this 3 is that 3. So here there's no coefficient, well, 1, so minus X. And over here, it's in my products, coefficient is 2, so plus 2X. Good start. That's my change. And I carry that change into where it says equilibrium. If I wanted to fill it out, I didn't fill this out in your chart, but I can just as easily say 0.400 minus X would be my molarity. And in this case, 0.600 plus 2X is my molarity. So it's basic algebra now to solve for my concentrations, and I have them put in your packet. I know that 1.00 minus 3X equals 0.352. It's a literal solve for X at this point, and I got X equals 0.216. That lets me solve for the other ones. That lets me calculate, as I've gotten your packet, showing that 0.6 plus 2X gave me 1.03 for my new concentration of NH3, and losing X from my 0.400 gave me 0.184 for my molarity there. It's easy to write your K expression from here because when we looked at the original reaction, we figured out which way it went. So you're going to get NH3 squared over N2 and H2 cubed. Put in your values and calculate to get a Kc for this of 132. If I wanted to go to Kp since they're gases, I'd be able to using the equation that relates Kp and Kc. Kp equals Kc RT to the delta N. And you're good to go. So for now I'm good with Kc. Follow through that example. Let's do another one. Let's do the practice problem there from scratch, and you'll have a chance below that to do some practice problems on your own tonight. Let's see what we've got. Oh, I was really nice on this one. I gave you the equation, so that's all we'll